Hello everyone, and welcome to this workshop. I am Anna Maria Christodoulou, and I am a doctoral fellow at the Rhythmo Center of Excellence at the University of Oslo. Here, I present a workshop that was created as part of my presentation at the 16th International Conference of Systematic Musicology in Sheffield, UK. Our topic is an introduction to multimodal music analysis using some of the most relevant toolboxes in MATLAB. Before we start, I would like to present to you some core concepts that will hopefully assist the greater understanding of multimodal music analysis as well as its significance in music research. First of all, it is important to explain what exactly multimodal analysis is. We define multimodal analysis as the study and interpretation of at least two or more types of data from different sources, or so-called modalities. Music research can involve the analysis of different aspects of music, such as audio, video, metadata, and many more, for a deeper understanding of the music structure. Multimodal analysis allows us to explore music from various perspectives, unveiling hidden insights and connections. For example, when we analyze a popular music video, we uncover a wealth of information beyond just the audio track, like the visual storytelling, the emotional impact through gestures, the synchronization between audio and video, and even the symbolism like visual cues and background selection. It also provides a holistic view of music, capturing not only the auditory experience, but also visual, emotional, and contextual elements. It is important to mention the significance of multimodal music analysis in music research to justify the reasons for which we are holding this workshop and understand what we can get out of such an approach. Analyzing audio, video, and motion capture data together provides a comprehensive understanding of a musical piece. Combining modalities helps us uncover the cultural, historical, and emotional context of music. We can reveal new forms of expression and storytelling and explain the enhancement of multimodal elements in music creation. Multimodal music analysis has many applications in music research, but also industry and education. Analyzing audiovisual information simultaneously can help composers create impactful scores for movies and media. Multimodal analysis aids in teaching music theory, appreciation, and performance. Artists use multimodal insights to shape their compositions and enhance audience engagement. Now, please allow me to introduce to you the three types of music data that we are going to work with today: audio, video, and motion capture. Starting with the audio data, this represents the sound of the music, including melody, harmony, rhythm, and vocals, and it is important because when we analyze audio, we understand better the musical structure, emotions, and artistic choices of a composition. For example, extracting features like pitch, tempo, and timbre from audio allows us to quantify and compare musical elements. Video data captures the visual representation of music, such as music videos, performances, and visual effects, and it adds an extra layer of storytelling, emotion, and context to the music. For example, analyzing visual cues, choreography, and cinematography reveals how the visual and auditory elements interact. Finally, motion capture data records the movement and gestures of performers or dancers, and it is very important because its analysis uncovers the physical expression and embodiment of music. For example, studying body movements, dance styles, and musical gestures or actions enhances our understanding of how music is physically interpreted. To give you a rough overview of what we're going to do today step by step, first we're going to implement an audio analysis, starting by a digital signal visualization, hearing our examples, and extracting some features related to dynamics, rhythm, timbre, and tonality. Then we are going to do a video analysis. We are going to watch our video example, do some basic processing, motion analysis, and we will visualize our analysis results. Then we are going to do a motion capture analysis, starting by plotting our motion capture signal, visualizing our figures, implementing some basic pre-processing techniques, and finally ending with some kinetic analysis. Let's start the implementation. We're going to use MATLAB, and this is a live script that was created specifically for this workshop. Our first step is to run the test to see if our toolboxes are correctly installed or if we have any errors. This is the result that everyone should see after running this test, and then we're good to go. We will start with audio analysis. This part of the script allows us to explore feature extraction and visualization from audio using the MIR toolbox. Audio data is essentially a digital representation of the analog sound wave produced by vibrations in the air. These sound waves are continuously varying in amplitude and frequency. In digital form, audio data is typically sampled at discrete intervals to capture these variations. To convert analog sound into digital data, we sample audio at a sampling rate measured in Hertz. By running the following piece of code, we can see the plot of the sound wave as well as the sampling rate of our file. This waveform has an amplitude of 0.5 and a duration of more than 90 seconds. Here we also see our spectrogram, which is a visual representation of our signal that changes over time. On the x-axis we have time. On the y-axis we have frequency, from low to high. The color or intensity of the spectrogram represents the strength of each frequency component. It's widely used in audio processing, speech recognition, and music analysis. A MEL spectrogram, on the other hand, is a modified version of a spectrogram that is designed to mimic how we perceive sound. Our ears don't perceive all frequencies equally. We're most sensitive to some ranges of frequencies than others. The MEL spectrogram takes this into account. On the x-axis we have time, on the y-axis we have frequency, same as before, but instead of a linear representation of frequencies, the MEL spectrogram uses a logarithmic scale called the MEL scale and groups frequencies in a way that's more meaningful to human hearing. To put it simply, a spectrogram is a way to visualize how the frequencies in a signal change over time, while a MEL spectrogram is a version of it that considers how we hear sound for more accurate analysis. Our example file comes from the Music Gestures toolbox, but before we proceed to the analysis and visualization of this file, we can use the MIR toolbox to hear it. Now, it's time to analyze our audio. First, we will investigate the dynamics of our musical audio. This involves quantifying and understanding various aspects of loudness, intensity, and volume changes within our piece. We can see that all the commands that we write, or so-called functions, start with MIR and continue with the type of computation that we want to do. For example, MIR RMS is an MIR toolbox function for the computation of RMS, or root mean square of energy. RMS is very commonly computed for various MIR tasks, and it shows us the level of perceived loudness. We can also compute low energy. Low energy regions in music often correspond to quieter or less active sections, such as intros, outros, interludes, etc. Identifying these low energy segments can aid in structural analysis, but also other tasks like music transcription, where we can focus our efforts on the most salient parts of the music. Moving on to the rhythm. Analyzing the rhythm of musical audio from a technical perspective involves quantifying and understanding various temporal aspects of the music, such as beat detection, tempo estimation, and rhythmic patterns. We can start by estimating the rhythmic clarity by indicating the strength of the beats estimated by MIR tempo function. So this function is calculating how many beats we have per minute. Here, the tempo related to our file is 109, approximately 110 beats per minute. Pulse clarity is a function that estimates the rhythm clarity, indicating the strength of the beats estimated by the MIR tempo function. Here we can see that we have quite low pulse clarity. Moving on to timbre. Analyzing the timbre of musical audio from a technical perspective involves quantifying and understanding the spectral and temporal characteristics that define the unique sound quality of different musical instruments, voices, or audio sources. We start by computing the attack time. The computation of attack time is useful in music and audio analysis as it helps characterize the sharpness and suddenness of a sound's beginning. Also, it can help distinguish between different instruments or even indicate a more legato or expressive playing style. The MIR events function is very important for the computation of attack time since it provides us with the onset curve, or so-called envelope of our signal, from which we can extract the peaks and perform our computation. Lastly, roughness is useful for determining audio quality or even for tasks such as instrument recognition. We will conclude our audio analysis by extracting features related to tonality. Analyzing the tonality of musical audio from a technical perspective involves quantifying and understanding the harmonic and melodic aspects that define the key and tonal center of a piece of music. First, we detect key strength, where we can see that we get an estimation of whether our piece has stronger correlation to major or minor modes. Then we can estimate our tonal center positions and their respective clarity. And for example, here we can see that our file has a high confidence of E major, and if we go back to our key strength, we can see that E major is a very high candidate here, but it would also be very useful to test this function with other files. For example, we can load a C major chord. We can see that C major is highly correlated here, and if we ask for the key, we get C major. Same with a piano loop in G minor. We see here that the key strength shows the highest correlation to G minor, and if we ask for the key, we get G minor. Video data in multimodal music analysis refers to the visual recordings of a musical performance, which can include video footage of musicians, singers, dancers, and the overall stage or performance environment. Video data plays a crucial role in multimodal music analysis as it provides a visual representation of the performance and can be integrated with other modalities such as audio, motion capture, and physiological data to gain a more comprehensive understanding of the musical experience. First, we are going to read our video file and then we are going to play it. We now move to some very basic video processing techniques such as cropping, rotating, and adjusting. This may seem a little low level or not that interesting, but it is very important for pre-processing our videos, but also it is essential in computer vision tasks for several important reasons. For example, real-world data can vary in many ways, so augmenting this data through rotation or adjusting helps the model learn to recognize objects or patterns in various orientations. We can also achieve data generalization, improve accuracy, reduce our bias, improve our training efficacy, etc. Proceeding to motion analysis, we start with computing optical flow. Using music gestures functions, we can obtain various motion information. For example, the optical flow function computes optical flow vectors, which represent the motion of pixels between consecutive video frames. This can help analyze the flow of movements in the performance. It is also possible to conduct the gesture analysis directly through video, detect and classify hand gestures using computer vision techniques and machine learning models in MATLAB, but also analyze the trajectories of specific gestures or hand movements to understand their spatial and temporal characteristics. These tasks require a bit more time, so it is outside of the scope of our workshop today. We can move to motion capture. So this part of the script will allow us to explore feature extraction and visualization from motion capture data using the motion capture toolbox. Motion capture data in the context of multimodal music analysis involves capturing and recording the movements of musicians, dancers, or performers during a musical performance. This data is typically collected using specialized motion capture technology such as optical markers, accelerometers, or depth sensing cameras to track and record the precise motion and gestures of the performers. Motion capture data plays a crucial role in multimodal music analysis by providing a deeper understanding of the physical expressions and interactions of musicians and performers during a musical performance. We will start with some very basic pre-processing, such as checking for missing markers and filling the gaps in our data. Missing markers result in incomplete data, which can lead to gaps in the motion trajectories. Complete data is essential for accurate analysis and reconstruction of movements. Also, missing markers can lead to incorrect assessments of joint angles, motion patterns, or other kinematic parameters, affecting the quality of the analysis. We can visualize our data in 2D, 3D, but also create an avatar. Moving on to the kinematic analysis, in the context of multimodal music analysis, it involves the study of the motion and physical movements of musicians, dancers, or performers during a musical performance. We will start by computing cumulative distance. This is a measure of the total distance covered by specific body parts or instruments or performers during a musical performance. It is a quantitative metric that quantifies the spatial extent of motion over time. It is calculated by summing the distances traveled by selected body parts or instruments or performers during a musical performance, and it can include the hands of a pianist, a bow of a violinist, the feet of the dancer, or any other relevant body parts or objects in motion. It provides a numerical representation of the overall movement and spatial engagement of the performer during the performance. We can use it to evaluate a music performance, conduct an expressive analysis, music gesture analysis, and especially when combined with audio and video data, cumulative distance data contributes to a more comprehensive multimodal analysis. Researchers can explore how spatial movements align with musical and visual cues, offering a holistic understanding of the performance. Here we can see that it returns a norm. So it's a structure type containing the number of frames, cameras, markers, sampling frequency of motion and analog data, the number of analog devices, the order of time differentiation of data. For example, we can have location, velocity, acceleration, crackle, jumps, you name it. the marker names of the data depending on the equipment and file format that has been used. Then, fluidity of motion refers to the smoothness, coherence, and naturalness of a performer's movements during a musical performance. It is a qualitative measure that assesses how well the physical motion of a musician, dancer, or performer align with the music being played or the choreography being performed. The higher the value, the higher the smoothness or fluidity. This value is useful when we want to assess the artistic interpretation of a music piece and the technical proficiency of the performer. And last, we have the period of movement, which estimates the period of movement for each marker and each dimension. It is also important to mention that there are plenty of challenges in motion capture data analysis. Combining motion data with other modalities requires careful synchronization and alignment of data streams to ensure accurate analysis. Motion data can generate large volumes of data, particularly in high-resolution motion capture systems, so efficient storage and processing is essential. Also, ensuring the accuracy of motion data often involves calibration and filtering to remove noise and artifacts. Finally, motion data can reveal sensitive information about individuals, so privacy and ethical considerations must be taken into account in its collection and analysis. In the realm of music analysis, the convergence of audio, video, and motion capture data ushers in a new era of understanding and interpretation. This multimodal approach allows us to delve deeper into the rich tapestry of musical expression, unraveling intricate details that might otherwise remain hidden. By fusing audio, visual, and kinesthetic cues, we gain a holistic perspectives on the art of music transcending traditional boundaries. The importance of multimodal music analysis lies in its capacity to reveal the nuances in performer expression, audience engagement, and the interplay between sound, movement, and emotion. This multidimensional approach does not only enrich our comprehension of music, but also opens the door to innovative applications across diverse fields, from musicology and psychology to education, virtual reality, and beyond. Through the synthesis of audio, video, and motion capture, we unlock new dimensions of musical exploration, redefining the way we experience and appreciate the world of sound and motion.